Okay, seeing as we're at 8 o'clock here Eastern in New York, 5 o'clock a.m. Pacific time, let's go ahead and get started. My name is David Stankiewicz. I want to welcome you to today's webinar session hosted by the IEEE Standards Association. Today's presentation is Elon Musk right? Are LIDARs a crutch? What I'm going to go ahead and do is kick things over to Apar Raj, who's going to deliver our presentation today. So Apar, over to you.
All right. Thank you, David. Hello, everyone. I am Apar Rajendran. I'm based out of LA, California. I've been working in industry, the automotive industry, for a little over half a dozen years, and currently I'm consulting to an enterprise as an enterprise solution architect to one of the major automakers in the field. My focus is mainly on the connected and autonomous vehicles and products. And yes, it's 5 a.m. We are yet to see the dawn for today here, and I'm all charged up and excited to talk to you all about today's topic, which is, as David heads up, it's our famous Elon Musk. We all know who that is, CEO, co-founder at Tesla, and founder, CEO, Chief Engineer of SpaceX. He's actually right by calling LIDARs a crutch and claiming that all who would rely on LIDARs will be doomed. He's definitely one of the genius personalities in the era. Yet his strong criticism against LIDAR created a wave of mixed responses and reactions in and around the industry, right? So I bet this would certainly be an interesting topic for today, and I hope you all enjoy it. So let's get started. So here's the spoken, right? Tesla's first autonomous day, around like 6 months ago, April 22nd, 2019. Here he goes. LIDAR is a fool's errand. Anyone relying on LIDAR is doomed. They're expensive and unnecessary. And then a bunch of them are required. And one is bad, you got a whole bunch of bad stuff. And then it's ridiculous, right? So at first glance, it looks like a biased opinion with prejudice. Well, it sounds definitely like one. However, some of the experts in the industry spoke in agreement with this statement, while others have different goals when it comes to LIDARs and how we put them to use. And why is there such a serious attention given to this specific statement? And what is the story of LIDAR and why that's become a sensational topic? And the answer is similar to how important human eyes are to a human driver. The world needs to be observed as is. When I say as is, that's the challenge we have, right? So any misreading on the scene might ultimately cost human lives. And our world is not a definite set of setups, which is easy to program, like a test environment. That's not the reality. It comes with the uncountable various environments and infrastructure which our vehicles need to observe, read it right, and pass through. In fact, researchers from Cornell University have announced a paper about the pseudo-LIDAR, and they also addressed Mr. Musk's comment, and they kind of agreed to him, inclined to his point when it comes to the expensive side of LIDAR. So let's get into details. So let's take a look at, before we get into technicality, let's understand why this is so serious and why we have to talk about it, right? So let's see some of the real scenarios what we have to deal with when it comes to self-driving cars. And so these scenarios are including what we are going to go through, but not limited to these. There's much more could be the scenarios. We have a side street and alleys like this, and where there may not be much signs or markings, and we have mud roads where the boundaries are not clear of the path that may not be clear. And we have underground, dim light parking lots and open parking lots, more humans walking around, and streets filled with children who are playing and jumping in front of the car any minute. And we have suddenly stopping school buses for loading, unloading, the blind spots where students pass by. We also have like 3-lane freeways, 6-lane freeways, the drivers darting right to left, vice versa. And we also have the great roundabouts in countries that nobody likes to go around but need to merge and split. And we have unconventional construction spots, right, with special markings. You never know how this is going to be. There's no one way of doing this. And so the car has never been experienced. It has to follow through human directions at times on the spot. We also, similar to that, we have roadside accident spots, areas, and racing motorcyclists and bicyclists who zip through when you least expect. And we have snow, heavy, rain, heavy roads, could be muddy roads, misleading tracks. Sometimes we also still enjoy those 100-year-old carriages, carts, and chariots. And then maybe different animals, horses, buffaloes, yaks, camels, even elephants in some countries. And we have this famous accident-prone railway crossings with different gates and maneuvers. And unavoidably, the immature, irresponsible drivers, or I call them lucky ones. In fact, much more scenarios we still live in this world with human traffic police guide intersections, a road with no signs, lane markings, fade away, and the list keeps going on. So, while setups are endless, the actual challenge here is only double-folded, I would call. What is a double fold? The first fold is the ability to capture the scene as is, with utmost quality. And the second fold, interpreting the scene as is with utmost accuracy. So when I say what does it mean in terms of technology or the methodology, challenge one is the actual tool. Scanners like cameras, we have Lidars, radars. They should be able to obtain the most quality snapshot of the scene every second or maybe multiple times a second, at least without a fail. And the second fold, the challenge, is putting the data that's being captured by these cameras, lidars, radars, and processing them, extrapolating the objects involved in the scene, and the speed that they move, and if there's an event that's happening to which vehicle needs to react or respond. This also demands the most accuracy to avoid any misreading and accidents. This is done through an AI-backed software system in the backend. So in the interest of today's topic, we're going to focus only on the challenge one, which is the ability to capture the scene mostly, and then we may touch base a little bit on the dependency, which is a challenge, which is the second part of the problem. So what do we have in hand to address the challenge, the number one fold? We have cameras, which captures the light reflections at one shot, like image, or the video at the rate of certain frames per second. And we have lidars, which sends light signals called laser to measure distance and the speed, shape at a certain level of intervals. We have radars, which sends radio waves to sense the objects in the way at a certain level of intervals. So each one of them employs a different medium or mechanics to observe the scene, which gives them unique advantage and disadvantage due to the nature of the medium they use. Also, due to the same reason, their performance varies and so their costs. While the mechanism varies, the challenge is the same on hand. It should be a reliable technology or methodology to read or scan the environment under good, bad, and ugly conditions, which is like daytime, nighttime, and other unfavorable weather, basically at all times. So having said that, let's get back to LIDAR versus the rest discussion. Like, take a look at the technology players who happen to rely on what technology. In other words, their strategy when it comes to employing these to achieve the accuracy and safety in the autonomous vehicles. So in the interest of today's topic, we'll focus on LIDAR and camera only today. Right. So this era, after the smartphone revolution every major company is trying to penetrate into the auto industry, especially the autonomous business. Even companies like Apple, Google, Amazon, pretty much everyone. However, let's look at some of the major automakers and pioneers and AI product makers who are in the business of employing these sensors, readers in their own ways. So if you take a closer look, you could see that there's only a few of them rely majorly on non-LIDAR technology, while the rest of the crowd heavily relies on LIDAR tech. First, the obvious Tesla, strictly no LIDAR. And I mean, they use cameras, radar, other kind of sensors, but not LIDAR. And we also have the collaborative initiative from Ford, Volkswagen, and Argo, along with the Argo AI, where they rely mostly on LIDAR sensors. So non-LIDAR sensors, the cameras. And similarly, there's another team, Daimler, Bosch, and Mercedes. They're also relying mostly on cameras. So leaving the rest of the crowd heavily rely on LIDAR tech in their prototypes, test vehicles, fleets, and so on. So this is just only a hand-picked companies. And know there are NIO, there's NVIDIA, there's a lot of other companies is trying to have their footprint. But just to give an idea, and the question here is what's up with the LIDAR tech, right? Why there is a diverse or mixed strategies that we witness among these automakers. So let's take a look at the LIDAR. So what is LIDAR? It's kind of like the abbreviation from light detection and ranging, right? So, and I'm sure the audience from around the world, where I live, if you're being from in a Silicon Valley, Pittsburgh, Boston, San Francisco, or any other cities where autonomous cars are crawling the streets, you might have noticed that there's overgrown gum tops like a ambulance, right? Looking gum top, like a spinning thing on the roof, right? The vehicle. That's a LIDAR. To have the most important piece of the hardware in the race to unlock self-driving cars for everybody, the public. So the LIDAR works much like radar, but instead of sending a radio waves, it emits pulses of infrared light, right? Or the lasers we call. The human eye is invisible and measures how long they take to come back after hitting nearby objects. It does this millions of times a second, so then compiles the results into so-called point cloud, so which works like 3D map of the world in real time. Map so detailed it can be used not just to spot objects, but to identify them, like what kind of object it is, like a car, or human, a tree, truck, bicycle, whatnot. So once it can identify the object, it can also identify what's going on between the objects. So the events or incidents, and the car's computer can predict how they will behave, and that's like how it should drive. Radars are reliable too, but don't offer the resolution that we're talking about here, needed to pick out things like arms and legs of the scene due to the long wavelengths of radio waves compared to the short wave lasers. And also, like, just to give you a quick comparison to cameras, on the other hand, they capture, deliver detail colorfully, but require machine learning powered software that can translate 2D to 3D, and then there's a lot of back-end work. However, LIDAR, by contrast, offers hard and computer-friendly data, direct information in the form of exact measurements, right? So making the processing of this data easier compared to other technologies. And not getting the, and you can see like that's why the LIDAR is at the center of the blockbuster legal case between Waymo and Uber. Not getting into details of this lawsuit, the point here is to take note of how sensitive and significant the LIDAR tech is being perceived in the game of autonomous industry. So let's see a little highlights of the LIDAR powered tech. So we can call it out as laser-based, which means it boosts details, shortwave, And distance focus, which means its objective is to measure distance directly, so speed, which leads to the third point, that the data captured from the LiDAR is directly interpretable to the computers, the system, because it comes with a lot of information already. And since laser has power to penetrate most of the unfavorable weather conditions, provide a great amount of visibility to our vehicles. However, it has its downsides, highlights, or should I call it challenges, as we speak. It may change, because it could be a matter of time before they could fade away, right? Or we addressed. So LiDAR tech is expensive. Not to our surprise, we're dealing with laser readers that can process a million times per second around the vehicle, right? 360 degree. And then low adoption, or in other words, like lesser footprints due to the first challenge. Not many automakers have figured out a way to make it as part of the mass production vehicles. It costs a lot. And due to the very same reason, even there's not much data available for learning from the test vehicles, because not many test vehicles out there. So there's more, the less that you put your vehicle out there, the less you study the environment. All right. And let's look at the journey of this LiDAR. I'm going to spend a little bit of time here quickly to give you the current status of the LiDAR development. We'll just go back a little bit, like 12 years ago, 2007. There were 6 vehicles made history, right, but successfully navigating simulated urban environment without a driver, we're talking about, behind the wheel. And 5 of them was supported by a LiDAR sensor being introduced by an audio equipment maker called Lidars. So we're going to focus on them. And they're still being crucial for self-driving cars. They're supporting a lot of automakers. And they're also trying to cut down the cost, but still fairly expensive. But there's a drawback with the mechanical design, because there's a high cost. What happens is that the LiDAR equipment, like it's mounted on the top of the car, as we see, or laser physically spins around 360 degrees, which is like an ambulance, right? And then several times per second due to a lot of moving parts, is durability, performance degradation, and need to be compensated with high quality maintenance. So, hence experts in LiDAR business believe the key to building LiDAR that costs hundreds of dollars instead of thousands is to abandon this mechanical design and come up with something new, something like maybe less mechanical, maybe like more solid state design. You can think of like how a standstill camera works, right? So there's no or very few moving parts, and could make the units much simpler, cheaper. Maybe we could adapt to mass production. So if you look at the original 64 laser LiDAR, cost whooping like $75 grand US dollars. And we also, even if you go scale down to 32 or 16 laser LiDAR, it still costs you $8 grand US dollars. So, and they're still working on some new, even a smaller unit, but still. But we believe that they promised that the LiDAR price might fall drastically in the industry overall, because everyone's looking at this major challenge to be addressed. So just quickly give you a highlight on the work in progress. The solid state LiDARs, the researchers have developed 3 major ways of doing this. It's called micro electromechanical systems, MEMS, and there's a phased array approach, and there's also something called flash LiDAR. So the idea is not to go detail, but just give you quickly the MEMS. It uses tiny mirrors, set up millimeters across, and to steer a fixed laser beam in different directions. The mirrors, they control the directions, so you can see different angles in the same way. And then the phased array is basically emitting the light in a different direction. You can change you can change the direction of the laser beam by adjusting the relative phase of signal that is released from each emitter. So we think of how you maneuver the motorcycle to left and right, and so it's just. And the last one is a flash slider. It's a flashlight is more like a camera, stands still, scanning up altogether, and it's just like blast the laser, and then it just captures the entire scene in a single flash. Well, each one of them has a little bit of disadvantages and challenges. They're still working on it, but I believe that would bring down the cost of the LiDAR. When it comes to accuracy, there's no doubt that it's the highest as we speak compared to cameras and radars alone. So let's jump to the other side of the coin, which is a camera-powered tech. So from photos to video, cameras are the most accurate way to create a visual representation of the world. And who else would know than humans? We take selfies all the time. Especially when it comes to self-driving cars, this is true as well. So the autonomous vehicles rely on cameras placed on every side because we need to cover 360 degree, but each one of them, and also a little bit more because they cover almost like as much as 120 degrees in shorter range. But some of them even focus just a narrow view to provide long-range visuals. And some cars even integrate like fisheye cameras. It's more like a wide, super wide lenses to capture the most of it, more like a panoramic view, but to give a full picture of what's behind the vehicle for it to park itself. Though they provide accurate visuals, right? Cameras have their limitations. They can't distinguish details of the surrounding environment. However, the distances of those objects needs to be calculated. Like I say calculated, mathematically, to know exactly where they are. And that's to be done through program. It's also more difficult for camera-based sensors to detect objects in a low visibility conditions, like fog, rain, nighttime, just similar to human eye. Also, processing camera capture data is not straightforward because all necessary interpretations need to be learned and programmed by algorithm-heavy machine learning software, many of which are not available to the level where we can certify or can be certified as fail-proof for public safety. And we can quickly look at how it works as well. So, camera, you remember like a few years ago we had like Kodak cameras, cost a lot, and then now you can even buy even more better quality cameras for a couple of $100. But in general, all of them work the same. And what's more interesting and challenging about cameras is about accuracy, right? So it's much more to do with the back-end software processing. So let's see how the software converts the raw camera images into a labeled three-dimensional model of a car's surroundings. An algorithm is considered success if it can accurately place a three-dimensional model. And then like the bounding box, you see the small boxes around the objects in a scene. The software typically tackles this problem in two steps. First, the images are run through an algorithm that assigns a distance and estimate each pixel, because all we're dealing with is it's a snapshot. And it can be done using a pair of cameras, and there's something called parallax effect. So you view the same object from different angles, and then you apply that effect to given status quo, and then you convert that and estimate the pixel distance using single camera. And a second algorithm uses a depth estimates to group pixels together into discrete objects, like cars, pedestrians, or cyclists. So let's look at the highlights. So we can call it out as all image. Even videos are like a frame of images. So image-based, which means it boosts details as well, because it captures exactly as is with the best conditions given. And it uses a technique called parallax to convert the 2D, 3D model to scene. which is only possibly by heavy data processor, the AI-powered software. Which led us to the third point, that the data captured from the LiDAR is derived after heavy processing, but this one you have to derive it. So the LiDAR gives a direct data, the camera you need to derive from the pixels. And that tells us the fourth point is that most of the cameras lie favorably on lighting conditions, weather conditions. There are some cameras, like low light cameras, but still, we need to have a better quality. And that tells us it's data-driven. If the data is compromised, the result is undeniably undesirable, right? I mean, we all know there are a couple of accidents happened with the Tesla vehicle, which is solely camera-based. So, looking at the major highlights, they are also inexpensive, which leads us to the second point. They are well adopted by most of the automakers, or at least the major players who have a heavy autonomous footprint in the market, which means there's a data everywhere from all the test vehicles and fleets, because the more data is captured, the better the system learns, which improves the overall software's accuracy and performance eventually in various conditions. So let's look at the journey of the camera, right? So we just talked about how where we started the old classic cameras and heavy, which is price heavy. Now we can get the cameras for like a couple of $100, even better quality. But we also have to look at the accuracy. So what happened? So the challenge here is not much to do with the camera itself, but how we process the data that's captured from the cameras. So the Cornell computer scientists focus on the second step. And then some other researchers also working on camera-only approaches. They represent the pixel data as a two-dimensional image, and then with distance as the additional value for each pixel. Because when you say pixel, like red, green, and blue, and then there's another value, distance, trying to mimic the data quality of what we get from LiDAR. And then they run these two-dimensional images through a convolution neural network, and just process and identify the different objects. So you train, and then it predicts based on its accuracy. So there's also called a pseudo-LiDAR approach. And we talked about initially, I mentioned that there's a paper released by the Cornell University researchers. So what the cool thing here, no doubt, is about how they have to do a heavy lifting to convert all these data into a 3D point cloud, but with that kind of data is generated natively by LiDAR sensors. So anyways, this pseudo-LiDAR data is fed into existing object recognition algorithms. They're designed to take a point cloud as an input. So the backend, when you have to do all this heavy lifting and trying to achieve the accuracy, what we achieve right now is like 30%. And then even if you try to merge with additional supportive information from other sensors, and even including LiDAR data, and go through the CNN neural networks, you can boost up to 66%. But LiDAR alone, the percentage is much higher, around like 80 over, not sure. But there are different, but definitely the difference is really significant. So having said that, we can crunch these information details and put these into 4 quadrants where we place LiDAR and camera tech accordingly. So if you take the accuracy on Y and cost effectiveness on X, of course, The bottom and left are negative, and then the other side is a positive range. So the cameras fall under the bottom right, where they fit in, while LiDAR tech falls under the top left quadrant, climbing great accuracy, but fall behind when it comes to the cost effectiveness. And it's no-brainer that we are not interested in the bottom left quadrant, but while we are curiously seeking the solutions to be on the top right. We want the highest accuracy, high accuracy, and at the same time, it must be cheap and should be affordable in the mass production level. When we talk about accuracy, also we need to quickly address the performance comparison. So there's definitely a huge gap between the performance of LiDAR and camera power systems, where LiDAR hits the top of the scale. However, to take the advantage of the data the cameras capture and its cost effectiveness, like we relate on them as well, because of they're affordable and there's a lot out there. They're capturing currently in every street they run through. They're collecting all the data. For example, Tesla does a lot of virtual autonomous miles. And how they do it is because their system is currently, as we speak, like running around cities and capturing the data and feeding into their hub. And they're running these simulated miles for other cars. So even though they're not autonomous cars, but they're just capturing the data, there's so much to learn from that. We also can certainly use both LiDAR and camera together to achieve even better results. But in that case, it's worthy to note that the better performance of results you get may not be nothing to do with the superior accuracy of LiDAR distance measurements. It's not about the ability to capture details, because they both do, and LiDARs will do a little bit more in the worst conditions as well, a little bit better. Rather, even though it's the case, but it's because the native data format that LiDAR produces, because it's happens to be easier for machine learning algorithms to work with. And on the other side, camera performance goes down. It only works in the convenient weather. And also the challenge on the LiDAR, we have to have less mechanical things going on, and then we have to have more solid-state LiDARs in practice. All right. Which leads us to a final section of our discussion on this presentation. So we're trying to answer the question here. So is it a crutch, or it could be a complement? So having said all this, right, and the question at hand is this. Before we assess any technology, whether it's a crutch or a complement, let's understand the fundamental factors, right, that would help us do that. And this is from my perspective. There could be many more, but what I try to summarize them to a high-level classification of the factors. And I call them like durability, reliability, cost-effectiveness, accuracy, and dependency. So what does it mean, like durability? I mean, how does the tool or technology perform in terms of its everyday usage? And reliability, I mean, how reliable is the tool or technology in response to various everyday environments, right, and scenarios? Because it has to succeed, it has to work, it has to be reliable at all times. And cost effectiveness, we all understand that. But with cost effectiveness, we're talking about how expensive it is to implement at the mass production level. And accuracy, and how accurate its performance at all conditions on an everyday basis, day after day, hour after hour, every minute on the road. or second. And the dependency. Is this tool or technology is being employed in assistance to other complement system, or the whole system is like laying it on like a sole backend tool, which could end up being a single point of failure. If it goes down, you're doomed. However, I personally believe that the top two factors among these actually flip the coin. That switch the game, right? Major role in such assessment, that would be cost effectiveness and dependency. So we talked a lot about accuracy, and why I didn't pick that accuracy is because it's not a question to be an option. In other words, we can compromise on accuracy. But that's not a challenge. We have to achieve it anyway. And then in safety also, it's kind of accuracy, more accurate and more safer. So, but what kind of, when it comes to assessing, if we want to tag them, a crutch or a complement, so it has to be these two. So let us try to conclude all these factors, right? By applying all these factors, they are applicable for LIDAR. As we speak, it has low durability and high reliability and high cost, high accuracy, and high dependency. Perhaps such a combo make LIDAR a crutch for now, right? However, time depreciates technology cost. So with the trend that we are witnessing right now in the industry, we believe to bring the cost and dependency significantly down, which would turn LIDAR into this combo: high durability, high reliability, low cost, and high accuracy and low dependency. So in that case, I believe that the complementary tech than a crutch. So that's my take. And well, before I end my webinar, since you guys are kind enough to stay to the very end, I would like to share tidbits in a few next level tech that's really hot in the market now. It's called IDAR. IDAR is like intelligent detection and ranging. There's a lot of companies trying to do this, and one of them is called AI. It sounds AI, but it's like AEYE spelled. Basically, the goal of IDAR is to enable self-driving cars to see what only matters by eliminating the noise. You know, in its first instantiation, IDAR takes a solid-state agile LiDAR, fuses it with a low-light HD camera, then integrates artificial intelligence to create a smart, software-definable platform that enables faster, I think more accurate, that's the idea, and then more reliable artificial perception. So how, like, our brain come up with this perception, right, understanding of what's going on. And by integrating the cameras and LiDAR, the AI equals a perception system, right? So that's better than sum of its parts. It's better than go by individual text. So it surpasses both human eye camera alone, which is what we're looking for, because we don't have the sophistication of the human brain yet replicated. That means we haven't figured out to have a system that can be in mass production as complicated and efficient as a human brain. So we need to invest more on how we can make it easy, how efficient we can work on the data and processing than the actual hardware itself. So the bottom line is this: currently, correctly implemented IDAR increases the speed of cars, artificial perception by up to 10 times. They're climbing, while reducing the power consumption 5 to 10 times. How they're doing is because they're decreasing how much data is conveyed to the motion planning system. They're cutting down to 90%, so which is great. So I'm just saying it could be one of the potential detection solutions we could look at. So please check it out. And with that, I would like to call it the day for the webinar and leave it to you guys. For any questions, before I stop, I'd like to take a moment to thank IEEE and Oxford for reaching out to me and giving this opportunity to present and providing me such an interesting topic. I enjoyed working on it and enjoyed presenting. I hope you all enjoyed as well. And thank each and every one of you for being a wonderful audience and appreciate any future connections. So this is my LinkedIn page. Please feel free to connect with me. Let's stay connected. And thank you, everyone.
Excellent. Thanks, Apar. What we'll do is we do have some questions that came in, so I'll take those in the order in which I got them. We'll leave this slide up for the duration. So if you wanted to jot down Apar's LinkedIn URL, you can connect with him, so that'll remain on the screen. Apar, I'll just go down the line here. First question that came in was, what is the best combination between LIDARs and cameras for A, the best accuracy, and B, the greatest cost effectiveness? And do you have any statistics that you can cite?
So it's a good question. I think it's just kind of addressed the last section of the presentation. So there are companies working on how we can get the best out of the both worlds. So given the current situation, the LIDARs are still expensive. So when we're talking about cost, we still have a long way to go. But when it comes to accuracy, sure. From a testing perspective, we can put them together and we can achieve the great accuracy. And now I just talked about IDAR. If you check it out, they're achieving it by cutting down the data processing of 90% of the noise. So you just focus on what is most important for the cars to process. Regarding statistics, I can try to get it. If you can hit me on LinkedIn, we can talk about it. So hope that answers the question.
Yeah, no, I appreciate that. And yeah, if the question asker for that particular one wants to connect with Apar for some stats, please reach out to him. Apar, we have another question here. It's in actually relation to the millimeter wave system. Someone asks, is the millimeter wave system a better system than the LIDAR vehicle mounted sensor in bad weather conditions? Can you speak to that at all?
That's actually a very detailed question. So the challenge right now is the spinning LIDARs is what we have. The Velodyne's mechanical design, right? So it spins around 360 degree, it captures and everything. The solid state LIDARs, they stay and then they just change the direction. And when it comes to weather, well, it's how we see because there's no mechanical interruptions. I mean, that's the whole idea of having the solid state LIDARs. But if you have anything specific, then we can talk about it. Because personally, I don't see, other than the core advantage of having the solid state LIDAR. In the question, I think, if you compare to anything else specifically in mind, or just compared to what we have in the industry and what we're trying to do with the MEMS, there's definitely an advantage. But if there's anything else and you want me to address comparatively, then we can talk about it.
Excellent. Okay. Let me see here. I have one more question. Yeah, one more question that's come in. If anyone has any additional questions, please use the Q&A tool and ask your question. This one is a little complex. Let me see if I can make sense of it. Apar, how would you suggest we handle low light performance with artificial intelligence algorithms using cameras when we know the rates of detection decrease in these particular types of situations. Can you speak to that a little bit?
Sure. That's a good question. That's actually one of the challenges we have with camera right now. So we do have, there's two ways to address. One is, as I always say, how we capture the data. So like we're trying to improve the tool itself, the technology, the hardware itself, trying to come up with the low light HD cameras, night vision cameras, and fish eye cameras. So we're trying to improve on that area, but also, as I said in the question, the second part, how we process the data, how we train them. So currently, because the nature of how the mechanics or the medium that the camera uses, the light signals, so all pixels. If we don't have the clear data, you just don't know what's going on. That's like a human eye problem. But then how researchers currently trying to address this is they use the other technology. That's where the other sensors come into play. And what they do is, well, one is a different angles. You can have multiple cameras, but if let's say all the cameras on the car face the same situation, same disadvantage, then you have other radars and LIDARs. So you take these data points and they kind of map it over the other ones and try to get a better perception of it. So that's one of the goal of the IDAR systems. They try to get, that's the artificial perception of the world, the 3D world they're trying to create by mapping, taking the best of both. Certainly, I'm sure even Tesla uses the other sensors in the data mapping to understand the low light and the challenging environment, challenging weather situation. Hope that answers the question.
So we did get, thank you, Apar, for addressing that one. We did get another question that came in. When it comes to, let's see, CNNs or convolutional neural networks versus the IDAR that you spoke about near the end of your presentation, which one has a better prospect, or can you go over some of the advantages of the two of those?
Well, when it comes to image processing, I mean, CNN was a breakthrough innovation. So how human eye, how our brain process, neural networks process that, and layers of information is extracted from the image through multiple neural networks. And the other one is you're talking about the IDAR. I mean, end of the day, they're all AI-backed systems. So, and when you talk about, we also say in the data science world, right? It's not who got the best algorithm; it's like who got the best data. So, it's all about what we capture. And you can have the best algorithm in the world, but if your data's quality and integrity is not there, then you're not going to achieve what you want to achieve. And that's still the case when it comes to the autonomous vehicles. What we are trying to achieve is most of the time to get that 3D point cloud data as close to what the situation, what the scene is. And that's the challenge we have. That's why we're doing this recipe thing and take this data from LIDAR, radar, cameras, and other sensors, and trying to feed this most useful information in a most useful format to these algorithms. So I think the answer would be more of how we can what better data format, and then we can feed the actual algorithm itself. I hope that answers the question.
Okay, thanks, Apar. Just looking at the queue for questions, I don't see anything else that's come in. So what I'll go ahead and do is just take us out. I want to thank again Apar for joining us today to deliver this presentation. I know he woke up very early on the West Coast of the United States to deliver this presentation. So thank you. Thank you again to the IEEE Standards Association. They are the host and they made this session today possible. So thanks to the IEEE-SA. And with that, I'll take us out and I'll ask everyone to have a great rest of their day. Thanks, Apar, and thanks for everybody for joining. Take care.
Thank you, everyone. Have a great day.
Bye now.